Good morning, Earth Science, and welcome back. Today we're going to be talking about Chapter 24 on the topic of the moving ocean. As you can see from this NASA image here, this way, uh, there is lots of there is lots of movement inside of the ocean. Um, it's not a big static pond as you think about it. It is a thing that has lots of currents and movement that is happening, and we're going to talk about some of those today. Okay, so the ocean is always moving, and we think about ocean movement as being waves. And waves are always happening on the ocean. Those are more of a tide and wind driven phenomena. But there is currents in the ocean as well. The same way that there's currents in a stream or currents in a river. Um, and this ocean current is going to be any continuous flow of water along a broad path in the ocean. So a big chunk of the ocean that's moving in the same direction. We have surface currents and then we have deeper currents, but surface currents are anything that's flowing in the upper 1,000 meters of the ocean. And these guys are usually driven by wind. So this picture here shows all of these really big surface currents. You can see that they're kind of moving in these like circular patterns in these kind of seas here. We'll talk about why that is. But remember that just like with air currents, these currents are going to be hot and cold, and that hot and cold differences is what's going to drive them to move in certain ways. We also talk about Coriolis effect because we have a large body moving a long way, and anytime that we have a large thing moving a long way, we have the Coriolis effect. So currents in the northern hemisphere, they're going to turn clockwise, whether that's going up or as they're moving across, then coming back down, and vice versa. Currents in the southern hemisphere turn counterclockwise. They go the opposite direction. So they're going against the clock there. Currents that are flowing away from the equator towards the poles are carrying warm water, and currents that are flowing towards the equator carry cold water. This is the same thing like we talked about winds. These cold currents are going to go to the equator, get warmed, and then move back north to cool down again as this continues to heat and cool and heat and cool. And this convection here. So these currents, surface currents, the biggest thing that's affecting them is the wind. There's two sets of wind involved in forming ocean currents. The big ones are the trade winds. These are the ones that are blowing in the northern hemisphere from northeast, and so from northeast means they're blowing down, kind of away from northeast, and vice versa in the south hemisphere they're blowing from the southeast. In the northern hemisphere here and in the southern hemisphere, both of these currents are pushing water from Africa over towards the Americas. Water is going westward in the Atlantic. As these winds go and they get affected by the Coriolis effect, then they start to get affected by the westerly winds. And westerly winds here, these are ones that are blowing from the west towards the east, and so they're blowing from the southwest in the northern hemisphere and from the northwest in the south hemisphere. And they are going to push what we call this up here is the North Atlantic Drift. They're going to push that current eastward. And then Coriolis effect in the continents are going to push it down south. Most of the time, seasonal wind changes are not going to affect ocean currents super strong, except for one really big exception, which are monsoons. They blow one direction in the winter and the opposite direction in the summer. This flips those surface currents that are on the ocean. They'll be going into land one season, and they'll be going away from land the next season. This picture here is for the Arabian Sea monsoon. This is a really great example of this phenomenon here, as we get these winds flipping, and when they flip, they bring rain. When they bring water in, they're warm. They bring rainy seasons, and when they're moving water away, they're colder. They make a dry season in these areas. Okay, so we said warm currents are moving from the equator away from the equator up north or down south. Warm water usually flow also to the western side of ocean basins. So the Gulf Stream and Kuroshio Current, here's the Gulf Stream here along the east coast of the Americas, and then Kyoshi Current is over. Kuroshio Current is over here. But places that have are around these and have water that is coming from them have warmer climates. So this is why up here in North Ireland, this warm Gulf Stream is bringing this warm water up there, and we have palm trees in North Ireland, despite it being really far north and shouldn't have that really nice climate. The big one here in the Americas that we talk about is the Gulf Stream. This is a really narrow, intense flow of warm water. Gulf Stream is right here. Begins in the Caribbean, and it follows the east coast of Americas up to about North Carolina, and then it veers across here and becomes North Atlantic Drift. And it forms this western and northern area of this large body of warm water that has very little wind that we call the Sargasso Sea. And Sargasso Sea is really important. It is home to this really cool sargassum brownish seaweed, which is really crucial to their environment and really crucial to a lot of the marine life that eats that. So, but the reason that this seaweed lives and is so prolific in the Sargasso Sea is because of these warm conditions here. All right, cold currents. So these are flowing towards the equator, usually on the eastern side of ocean basins. And a great example here are the Canary currents in the North Atlantic or the California current here in the West Coast. So they can also flow out of regions that are farther north than that. And when they do, like the Labrador current here, it is bringing these big icebergs from way up north down into trade routes. And so that can cause danger to ships. It can cause cooling of that water. When you get the Labrador current coming down right here, matching up with the Gulf Stream here, you get really, really thick fogs. And that's why Newfoundland here has really, really thick fogs as this cold current is matching up with this warm current. And we have a lot of condensation happening as that air, that is, the water that is in the air is getting pulled out into fog. So Gulf Stream rings, like any other current, if you're watching a river and you see a little eddy forming, or you see like it kind of flow a different way really quick, ocean currents do the same thing. They don't always flow in the same channel. They wander off, they send off offshoot streams, they have these weird meander looking things going on. They have eddies and whirlpools, sometimes right on the main current itself. When this happens, these are going to break the current, and they're going to be called what we call Gulf Stream rings. And there are two types of Gulf Stream rings, and they're determined based on their temperature. So as these rings form, they're going to take some of this whatever it is and then move it away from it. So in this case, it's going to take this warm water and move it up towards the continent, towards that colder area. And in this case, it's going to take some of this cold water and move it down. So a ring that's forming on the Sargasso Sea side of the Gulf Stream. This is a cold core ring down here, so if it's forming on this side down here, it takes some of the cold water from the continent side and forms a cold core ring. Or vice versa, if it's forming on the continent side of the Gulf Stream, it is going to take warm water from the Sargasso Sea down here, and it is going to move it up and around into that area up there, and it's going to be called a warm core ring. Now, most of the time in one of these systems, 10 to 15 rings are forming each year, and most of them are very short-lived, a couple weeks, but some of them can be persistent and last for up to 2 years. And then the last thing inside of a 24.1 here is countercurrents. And these are currents that flow in the opposite direction of the wind. So we talked about these westerlies blowing really strong here. This little countercurrent in green here is moving against that. Countercurrents, they can flow at or beneath the surface of the ocean. And the example here that we're looking at is the equatorial countercurrent. They're surface currents. They're within that first 1,000 meters of ocean. But the reason they happen is because as these westerlies flow really, really hard, all of this water keeps getting pushed over to the west side of these ocean basins. Enough so that there's a strong enough gradient of more water over here and less water over here that this countercurrent starts to form to bring water back to this eastern side here. So really cool. This current is forming to kind of equal out the ocean and make sure that there's enough water to continue to have these currents flowing. Um, very fun. The countercurrents, equatorially speaking, are bigger in the Pacific but occur in the Atlantic and Indian Oceans. And they don't only appear on the equator, but these are where they're most common and most prolific. So, all right, the next topic we're going to talk about are currents under the surface. So we talked about surface currents. They're going to push a lot of what goes on underneath the surface too. But deep ocean currents themselves are not wind driven. Instead, they are driven by gravity and differences in gravity and density. A density current, this is a water mass that is heavier and denser than surrounding water. Because of this being heavier, they're going to sink down to the bottom of the ocean and can be at the bottom of the ocean and circulate between 500 and 2,000 years before they recirculate back up to the top. Density currents can be found in all the world's oceans. They connect with warm global surface currents, and they are the system that mixes this hot and cold water of the oceans. And we call this system and this big long chain of all of this the global conveyor belt that moves things around the planet. Density currents are slower than surface currents. They're not moving as fast because they're relying on slower, forces like gravity and density instead of the wind. But they're very important nonetheless. They're important to marine animals because they retain oxygen that these currents absorb at the surface. They also retain the temperature and salinity that they acquire at the surface. And they're the only oxygen source for deep sea life, and they're a good source of nutrients for deep sea life. These density currents can also flow vertically to either drag sand, silt, and soil down to the bottom to create nutrients, or when they come back up from the bottom, they bring nutrients with them from the seafloor. So they can go sideways as they flow, or they can go up and down as they return or go into the depths there. So we get density currents several ways. The first and the kind of the easiest to wrap the head around is from polar water. When you get polar water here, it's very cold. As water gets cold, it gets dense. It gets denser than regular water, right around 4 degrees. So cooling water causes this to contract. It takes up less space. It becomes more dense. When we get structures like icebergs, the water that freezes into ice doesn't take its salt with it. So all that salt that was in all this water in this iceberg is getting deposited into the water here. And then as it does, that water becomes saltier, becomes colder, becomes denser, and it sinks down below the surface. There are three cold water masses and great cold water masses where most of our cold water is coming from. And they are in order here of coldest down to warmest. The first is the Antarctic bottom water, coldest, densest water in the oceans. There's lots of cold water from the Weddell and Ross Seas. The average temperature of this is negative 4.4 degrees Celsius, and it has a salinity of 34.6 PSU. Getting a little bit warmer here, we have the North Atlantic deep water. This is the second level here. It forms near Greenland and then sinks down. It has an average temperature of 3 degrees Celsius and 34.5 PSU, so a little bit less salty. And then we have the Antarctic intermediate water here, and it's the least cold of these three masses, and the least salty of those three masses. Another way that we can get density currents is they can be caused by evaporation. When we have warm, dry climates, when the water evaporates, it leaves the salt behind, and the water density increases. So areas that have more evaporation than precipitation can get this. The Mediterranean itself is a really great example, as it has more water evaporating than is receiving from rainfall and rivers. If you're familiar with the Mediterranean, you know the Strait of Gibraltar connects the Mediterranean to the Atlantic Ocean. On the Atlantic side, it is 35 PSU, pretty much the regular salt of the ocean, and the Mediterranean is 40 PSU of the saltiness. So it ends up being much saltier and then much denser. So this dense salt water flows out of the Mediterranean and then goes down into the depths there, goes underneath of the Atlantic water. And then this water, actually, the Mediterranean as it comes out of there, that current forms branches of streams that are larger than the Mississippi River, and these branches have been traced all the way out to Greenland and the Bermudas. So this water is traveling a long ways from the Mediterranean as a deep density current there. All right, upwelling. This is when we have cold water that's coming up to the surface. It is common on the western side of continents where the wind's blowing along the coastline toward the equator. What this ends up doing is this pushes all the warm surface water away down towards the equator, and then the cold water gets pulled up from underneath to replace it. Places that this happen are the California coast, Morocco, Peru, Australia, on the west coast of Australia. So we're getting all these west coast things happening, and that's causing a lot of these upwellings. Upwellings are very important. They contain lots of nutrients that phytoplankton need to grow. And then whenever we get an area that's upwelling, we get lots of fish and lots of other animals up the food chain that are eating the phytoplankton. And then these areas in turn are usually commercially fished because that's where the fish are. We have lots of fish around these upwellings. So knowing where they are, if you're a fisherman, could mean that you get a good haul that day versus not getting a good haul that day. The last thing we're going to talk about in this chapter is tides. Tides are the periodic rise and fall of the ocean due to gravitational pulls of the moon and sun. We talked about waves here. Waves are normally caused by wind, but the tides, that up and down of the water, is caused by the moon and sun. So both of the moon and sun affect the time and height of the tides, and this has a really profound effect on people who live on shorelines. And if you live on the shoreline of some ocean, you are probably pretty well aware of what the tides are, when the tides are going in and out, and what that means for you. So tides, they go in and out several times during the day. When tides reach the highest point, like on this picture up here, this is called high tide. And then when they're down at the lowest point, this is called low tide. This is the same area here. This is the Bay of Fundy. We'll talk about it later. It's a really cool area for tidal activity. So the tides, the big one that forms it are the moon. And it forms it when we get a new moon or a full moon. So when the moon is here or when the moon is here. And we've known for centuries that that's true. We know that just anecdotally that whenever the moon is full or the moon is new, the tides are stronger. But it was actually Sir Isaac Newton that explained that it was the gravity of the moon that was causing tides. So when you have two objects in an area, they're strong. The gravity between them is stronger if they're closer together. So when the moon pulls on this side of the Earth, which is the closest side, it pulls on this more than the center of the Earth, so this water bulges out and creates this high tide bulge here. On the other side of the moon, there's another tide. We have another high tide over here. This is because the moon is closer to the center of the Earth now than the moon is to the water out here. So the second tide is actually caused by the planet being pulled away from the water. The first one, the water is being pulled away from the planet, and the second one, the planet's being pulled away from the water. If you're on a side that isn't there, this one in this case, you've got low tide for that part of the day. The moon, as it sets and rises in the sky, it rises 50 minutes later each day, and so the tides move 50 minutes each day. And they'll go all the way through a 24-hour cycle. The sun itself has a lot of effect. It has a lot of gravity because it's a lot bigger, but it's a lot farther away. So the sun only affects the gravity of the tides on Earth by about half as much as the moon. But it can enhance or detract from the moon's effect, making the tides either greater difference, or like higher high tides, higher low tides, or less high and less low. So when the sun is in line here, like it is here, either a new moon or full moon, the high tides are especially high, and the low tides are especially low, because all of this water is getting bulged either towards the moon or towards the sun there. This process happens twice a month, and they are called spring tides. Is the name that they've been given, just because they're usually a little bit more dramatic in the spring, but they happen year round. The other kind here is neap tides. These are when the moon is in its quarter phases, the first and third quarter, and the sun subtracts from the moon's tide-making ability. The moon's wanting to pull this bulge out here, and the sun's wanting to pull this one out here, and so it ends up being more round all over the Earth. So we get high tides that aren't very high and low tides that aren't very low. And these tides also happen twice a month. Another thing that affects tides is the moon's proximity to Earth. As the moon revolves around Earth, its proximity to Earth changes. It is, when it's closest to the Earth, it's what we call the perigee, and it is greater tide effects, especially during spring tides. You're going to have higher high tides and lower low tides. And if the moon is the farthest away at the apogee, we're going to have the tidal effect being less. There's going to be not as high tides and not as low tides. It's going to be kind of stay the same during that time. A number that we care about, that we talk about a lot, is tidal range. When you're out sailing on the ocean, it's not noticeable that the ocean is going up and down. But when you're on shore, and you have something to compare it to, it's very obvious. The difference in water between the high and low tide lines here is what we call the tidal range. The tidal range can change all the time, every day, and it varies from one body of water to the next. If you're on a small lake, there's very little change in tidal range. It's not a big enough structure, it's not a big enough body of water to be affected by the moon's gravity. If you're on a really big lake, like one of the Great Lakes, Lake Superior, the biggest of the Great Lakes, goes up and down a few centimeters. So still very like 1 inch, very, very small, probably not even noticeable unless you're like really looking for it. And then on the open ocean, you have an average of 1 meter between high tide and low tide. We really look at, and if you're spending any time on a coastline, you're going to be interested in the tidal range on shore. They vary from place to place. If you're in the Gulf of Mexico, where you have a really broad beach, the tidal range is 0.5 meters. If you're back here in the Bay of Fundy, which we've already talked about and kind of introduced in Nova Scotia, your tidal ranges can be 20 meters difference from way down to way up. The difference in these is the width of the shoreline and how far apart this water is spread during low and high tide. The Bay of Fundy here, it has this little V that you're not quite seeing here out here, but all the water comes in there and it has a hard time getting out, and so it continues to come in, and you get this really profound, really dramatic event where you get this really cool coastline here. So, but this is the conclusion of chapter 24. I hope you learned something from this chapter. I hope you enjoyed it. If you have any questions, let me know. We'll see you in the next one.